In Pennsylvania, a catastrophic landslide rocks a community.
The entire slope started to move, the roadway cracked at the top, all of that material is now pushing down slope.
Disaster strikes at the heart of a small town in Iowa.
It was a very scary moment. You just couldn't believe it. I mean, how can this happen?
In Indiana, a bridge build goes tragically wrong.
They was laying concrete about 40 feet into the air when a disaster struck.
And in the UK, a state-of-the-art highway project threatens chaos.
There is a technological room for error, and there's also a human room for error.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineers take on gravity, strong foundations and perfect balance are everything. Just one slip-up can lead to catastrophe. Like this disaster in rural Iowa, a big day for a small town that went horribly wrong.
Everything looked to be fine, then the crane just went down.
And the whole crane fell on the structures and everything fell to the ground with it.
This engineering error came from nowhere and left residents reeling.
The steel girders, the crane itself were all laying across here.
The rolling green state of Iowa is home to thousands of farming towns like New Providence. Dennis Reese has lived here for more than 30 years.
Well, right now we are walking down Main Street of New Providence, Iowa. New Providence is a typical small Iowa town, originally settled by the Quakers back in the mid-1800s.
Like many rural communities, New Providence is proud of its water tower, which has carried the town's name for 2 decades.
There are water towers all over the world. They're not just for storing water. You can do that easily at ground level. The reason for putting it up high is all about pressure. Gravity pushing down on the water gives the whole town a nice, consistent flow.
Water towers are important because they provide better water pressure, but they also are a backup supply system in the event of an emergency.
For decades, Dennis and his neighbors relied on water that was pumped in from across the state. Then, in 2000, they received major news.
New Providence had always had a water system for a long time, but it did not have a water tower. When we first heard that a water tower was actually going to be installed, that was a big deal for the town because it felt like we were going to be a real town now.
On July the 19th, the wait was over as the construction team rolled into town.
Well, it looks like somebody's coming down the road right at me.
One of Dennis's neighbors filmed the project from the beginning.
That's where the water will all be.
The plan was for the 4-legged tower to stand almost 40 meters tall, topped with a near 230,000-liter tank. Storing water so high meant gravity would ensure each resident had plenty of pressure. Like every building project, this one would be unique. Based on the location and type of lifts required, contractors brought in a mobile tower crane nearly 200 feet tall. With a crane this size, preparation was vital. Professor Risto Rautiainen is an Iowa-based engineering safety expert.
Every lift is a little bit different, so it takes a lot of careful planning, and it is definitely very dangerous. You need several people, some up on the structure, and often this is done at a height of over 100 feet, 30 meters, and so it is definitely very dangerous, especially when the conditions and the situation changes every time with every lift.
As with every lift, stability was key to safety.
Weeks earlier, they dug and filled a huge pit with compacted earth to create a solid base to build on.
So the very basic thing with cranes is you have to have it on solid ground and you have to set it up so that it is not going to fall. Usually when you set up a crane, you have outriggers to provide a larger base for the crane and what the crane is lifting.
Outriggers are telescopic steel arms on each corner of the crane with feet on the end. To spread the load out more, these were placed on wooden beams called cribbing timbers.
The first job was to raise the tower legs into position.
The empty tank weighed 14 tons, but when full of water, it would top 200. So the tower and its foundation had to be strong.
Once the tower frame was complete, the team lowered the water pipe into place. All that remained was to lift the tank.
Construction took several days to build the base of the tower, but then when word got out that the actual tower was going to be lifted into place, that was a big deal, and a lot of people gathered to watch the tank actually being set on the legs.
For maximum stability, contractors maneuvered the giant crane right up against the tower legs. Once in place, the outriggers were deployed to spread the load as wide as possible. The crane was so close to the tower that the rear right outrigger and its cribbing timbers sat on the newly compacted foundation. Now that everything was in place, the team started to lift the tank.
Well, they say we're going to lift off.
With the tank 40 meters up in the air, the crane rotated to line it up in position.
Just as the tank was being set on the legs, that's when things started to shift and move. The water tower and tank fell that direction. There's a tree that's still standing and has a scar on it. That's where the tank came to a rest, and then all of the steel girders and the crane itself were all laying all across here.
Two of the three workers were injured, yet tragically, their colleague was killed.
It was a very scary moment. It was a tragedy for the town. You just couldn't believe it. I mean, how can this happen? The obvious tragedy is that there was a loss of life.
The town was in shock, and as word spread of the disaster, the state launched an investigation. Engineer Risto Rautiainen was part of Iowa's fatality assessment team.
The main purpose with our program is to find out what happens in these kinds of cases and how we can prevent it again. My role was looking at it from an engineering perspective with all of the evidence we could put together.
With some investigation, it could take years to unpick what caused the accident. Was it equipment failure? Was it an operator error? Was it the weather? But here, one potential suspect was right in front of them.
The cribbing timbers from the outrigger beneath the tower had sunk and separated.
This site had been prepared fairly well some months earlier, but the soil layers on top were not really very stable. When it was time to bring the crane to this site, the top layer of the soil was quite wet.
Before every lift, engineers calculate the pressure a crane will exert on the ground and the ground's ability to withstand that pressure.
But here, the calculations were based on a flawed understanding of the strength of the ground.
The basic issue was that the pressure handling capacity of the soil was not adequate for the very high pressure that was put on when the crane was lifting the water tank and swinging it to a position, so the pressure was probably 2 times more than what the soil can handle.
Based on this calculation, the cribbing beams supporting the outrigger needed almost double the footprint to withstand the pressure. And as Risto demonstrates, the situation was made much worse on the weak soil because the timbers weren't secured together.
Now we're going to test if this outrigger setup in a miniature size will actually hold the weight of a skid steer loader. Okay, let's go.
The post represents the outrigger foot, the skid steer, the weight from the crane. And here, just like the accident, the cribbing clearly fails.
So we could see that when we put some pressure on, this timber started to dig into the ground and the others started separating, and finally it all fell and went through the timbers, and we can see how the soil behaves when it's wet. It really has no support if the pressure is put on a very narrow, small area.
As the crane turned to position the water tank, its weight shifted to the outrigger on softer ground. Then gravity took over.
All of the weight was put on just one outrigger, and that outrigger was not supported properly, and it sank into the ground, and the whole crane fell on the structures, and everything fell to the ground with it.
This fell quickly snowballed out of control. Once the crane started to tilt, the outrigger failed, and there was nothing to stop it from toppling.
Now, Risto shows how bolting the beams together and giving them a larger footprint could have made all the difference. The same ground conditions, the same weight from above, but a very different result.
So we have it on pretty wet ground here, and it is sinking just a little bit, but it is holding the weight because it is spread on the fairly wide surface here. Yeah, this is basically working now the way we would expect a well-designed turbine to work.
Back in New Providence, with the tower and tank destroyed, the only option was to start over.
After a disaster like this, lessons would have been learned. And when the new tower was built, everything would have been checked and double-checked to make sure nothing was missed.
Today, the new tower still stands as a reminder of the tragic events of 2000.
The fellows that were working on the tower actually were here quite a while in the area, and people got to know them. They were just doing their job.
This really was a tragic case that I think everybody in the area remembers for as long as they live, and we would really want to make sure that this kind of a thing does not happen again.
In big construction, engineering and the environment have to work together in perfect harmony. Get that balance wrong and the results can be catastrophic. Like this disaster in Pennsylvania, a vital hillside highway destroyed in just minutes.
The entire slope started to move, the roadway cracked at the top, and all of that material is now pushing down slope.
A race against time to avert disaster.
We need to do something immediate to get the local community out of harm's way.
And the ongoing battle to hold back the might of Mother Nature.
There was that much force. It took down the entire hillside, most of the road, all the apartment complexes below, totally destroyed.
Pittsburgh, Pennsylvania, home to US Steel, with a rich history as an American industrial powerhouse. Thanks in part to the landscape surrounding it.
Pittsburgh is famous as the Steel City. The slopes around it provided natural resources, including wood and coal, for the foundries that made this the nation's steel capital.
Nestled in the Allegheny Mountains and at the junction of 3 major rivers, the city's growth was complicated. District Executive of the Pennsylvania Department of Transportation, Cheryl Moon Siriani explains.
Pittsburgh was not an engineered city, it was not a planned city. It was a city that just developed from the industry. The industry grew along the river. Over time, if you wanted to work or live in Pittsburgh, you had to move outward.
As industry and infrastructure boomed along the valley floor, residents took to the hills. Local geologist Matthew Morris explains.
As the city expanded, residential development started to take place up higher on the slopes, and what that left was building roads to get people from the bottoms of the hills to the tops of the hills.
One of the most important is this, Route 30, a vital link between the city and the suburbs.
It's about 30,000 vehicles a day that utilize this route. So this is a major connector or collector that collects folks from the suburbs of Pittsburgh into the cities.
First opened in 1928, this stretch of road high above the city proved to be a challenge for engineers.
If you want to build a road on a hillside, you have various options. You can tunnel, you can blast into the rock, build a ledge for the road, or a combination. But if you do build out, one thing is crucial, a solid retaining wall.
Without a retaining wall, the slope could simply collapse or slip onto the land below. Geotechnical engineer Brian Heinzel explains.
The original wall was concrete cantilever structure. It has a shallow foundation footing, and then the soil on top of that footing helps resist lateral forces just by the weight of the soil over top of the footing, so it does not rotate.
Incredibly, this seemingly insignificant wall was the strength and last line of defense holding back this stretch of Route 30, in an area that is well known for landslides.
In our district, we have about 100 active landslides at any one time. There's some warning signs. You may see trees leaning, rock falls, excessive flooding, but it's honestly, unless you have a crystal ball, it's very hard to tell which road is going to go first.
With all of these steep slopes around here, you do have a lot of landslides occurring where you run into weak rocks, and over time the development encroaches more into those slopes, and as that happens, things start to destabilize a little bit more. I don't know that it's a great place to build a city, but it was the only place at that time.
In early April 2018, reports surfaced that Route 30 was starting to slip. Even for someone with 25 years experience, what Chief Engineer Brian Heinzel discovered was shocking.
We noticed that the guide rail was starting to move laterally. There was a retaining wall that had separated in one area. We also observed movements actually above and below the wall that were indicative of a landslide.
Cheryl Moon Siriani received an emergency call that something was very wrong.
It was Friday, April 6th. I was in the office, was notified by the assistant district executive that they felt there was an imminent failure. Time was definitely of the essence. It was most important for all of us that the traveling public who traveled along Route 30 and the folks that lived below were evacuated, and the road was closed immediately.
This situation was accelerating rapidly, so it was, best to try to get everybody out of harm's way. And in this case, it was lucky that we did.
At around 6 a.m. on the morning of Saturday, April the 7th, a 90-meter section of Route 30 dramatically collapsed. 2 apartment buildings and 1 residential home were completely destroyed.
And honestly, the slide occurred within hours after moving the people out.
More than 25,000 cubic meters of debris came crashing down in minutes, and the scale of the disaster became clear.
The whole roadway had collapsed. It fell about 20 feet. The slide mass had pushed the retaining wall and debris into the building, basically demolishing the building where we're standing right now.
This whole entire hillside was laying on top of the 2 apartment buildings down below. That is the first thing I saw when I got here.
While the quick thinking of engineers wasn't able to avert the disaster, it almost certainly prevented tragedy.
The damage was catastrophic. You could tell right away that, if anybody was still in those buildings, they would have been hurt seriously.
Some of them watched their entire world collapse in a couple of minutes, so that was tough.
The team had been monitoring the road for months and knew the ground was shifting, but they hadn't expected such a catastrophic fail.
We have quite a few roads around the area that are settling. It's sometimes due to pipe failure, sometimes due to bad soil underneath. So we kept adding asphalt to the road, thinking maybe it was just a settlement issue, not realizing there was a bigger problem underneath.
Engineers suspected the bigger problem might be due to local geology, specifically stony shale and clay rock. Geologist Matthew Morris explains.
Those areas where the shales and the claystones come out onto the slopes, they weather faster than the sandstones. And then that becomes problematic because those weaker rocks and weaker soils, you're now interacting with them as you cross over them with your, roadways, railways, any sort of a transportation corridor, really.
But it turned out geology alone wasn't to blame. The seeds of this disaster may have been sown decades earlier.
A lot of these roads were not engineered roads. They were roads that grew up from horse trails and farm field roads. The roads can't handle the additional traffic, the heavier weight trucks, and they fail.
Not only was the increased traffic load a problem, it appears the already unstable conditions were made worse by unusually bad weather.
Typically, we have around 38 inches of rain a year. 2018, we had about almost 58 inches of rain, and we did see landslides occurring much more frequently than what we had seen in the several previous years.
The weather in the months before the disaster added to that risk. There was a wet and cold winter and a big April snowstorm. All of this made the ground much more likely to slip.
So the weather triggered more landslides. But why did this one road fail so catastrophically?
Some of the catalysts were the weak claystone, the excessive amount of rainfall contributing to additional load and weight on the existing retaining wall.
After decades of increasing load from above, the old wall simply couldn't withstand the pressure any longer.
We believe that the final straw was the wall that was below, that was right behind the apartment complexes, did finally fail. That was kind of the last thing that was holding up this hillside, and then the whole entire hillside fell right after that started to move.
Gravity had been working away at the hillside for nearly a century, putting more and more weight on the retaining wall. The wet and cold weather just gave it that final devastating shove.
With Route 30 out of action and traffic diverted, authorities immediately went to work rebuilding this vital artery.
We were here basically 24/7 to help guide some of the emergency response.
Once the debris was cleared, work began on this, a new 120-meter long, 6-meter high retaining wall. Brian Heinzel was the project manager on this nearly $7 million build.
The wall was constructed by drilling 25 feet into durable sandstone bedrock and then filled back to the surface with high-strength concrete to support the beams. These panels here are reinforced concrete, and the anchors consist of steel cables there to provide additional support for the retaining wall against bending.
For added strength, the entire wall was backfilled with a rock embankment to ensure nothing was sliding anywhere again.
This wall is new and improved over the old concrete cantilever wall, and it should last more than the next 100 years.
While this area will always be prone to landslides, with a new, robust and rock-steady retaining wall, the only thing that's moving on this road is the traffic.
This disaster was a clear reminder of the constant battle between big engineering and Mother Nature.
We closed the road on April 6th. and we opened it back to traffic on June 27th, which is literally a miracle. That is his testament to the great people of Western Pennsylvania, having everybody working together. That's how fast this road opened back up.
Engineers have been working with concrete since Roman times, but even with the best known materials, just one mistake can have devastating consequences. Like this disaster in Indiana, a catastrophic collapse on a new highway ramp.
It was one of the biggest industrial accidents in history.
A seemingly simple oversight with disastrous results.
It's a very unfortunate sequence and an incident, losing life. What a tragedy for us.
The obvious question, what had gone so fatally wrong? East Chicago, Indiana, sits at the southern tip of Lake Michigan. Once swampland, the city grew into an engineering powerhouse, nicknamed the Workshop of America. Michael Puente is a local reporter.
East Chicago is a very industrial city. You are not going to find too many cities in the country that is this industrial. But it's also comprised of a lot of great people, a lot of down-to-earth, blue-collar families.
East Chicago is known for one thing, heavy industry, particularly steel. More than 100 years ago, the Indiana Harbor and Ship Channel was built to help move it all around.
A lot of the products that are made here are shipped to all parts of the country and even world. It's a very important cog to America's industrial might.
In 2020, this elevated freeway, known as Klein Avenue, was completed to streamline the flow of industrial traffic through East Chicago. But this isn't the first Klein Avenue viaduct here. Although its predecessor was built 4 decades ago, it worked the same way.
The Klein Avenue Expressway was a long section of elevated road, basically a long line of bridges up to 100 feet high, including a main span over the ship channel.
I was in junior high school at the time. The construction was underway to build the original expansion bridge. It was deemed one of the largest construction projects in the history of Indiana.
Back then, engineers chose a tried-and-true technique to build the more than 5-kilometer-long viaduct, with concrete for the decks poured in their final position, called cast-in-place. Gongkang Fu is a professor of civil engineering.
Cast in place meaning we cast that bridge right here, not in a shop, and then move the parts to here to assemble.
With cast-in-place bridges, molds are built between the piers in the shape of the bridge decks, with extra support coming from temporary structures called falsework. After the concrete has been poured and fully cured, the falsework is taken away, leaving the bridge section behind.
When the concrete was cast first, it's wet. There's no strength. We have to wait for 28 days for the concrete strength to build.
In 1982, this cast-in-place construction was in full swing, both on the main roadway and access ramps that would carry traffic up from the industries below. April 15th, about 75 workers were on site, some more than 20 meters up in the air, preparing to pour the concrete for a new span.
One of the most dangerous moments for cast-in-place construction is when the concrete is being poured. Suddenly, the structure has to carry all that extra weight.
At 10:40 a.m., the concrete pour was underway.
As it was going up and they was laying concrete about 40 feet into the air when a disaster struck.
Suddenly, the falsework crashed to the ground.
These sections, when it collapsed 400 feet, it crushed several people.
Just minutes later, the adjacent spans fell too.
Unfortunately, there was no warning. That was very devastating. Co-workers watching their colleagues standing there without any help, but they couldn't help either.
There has been big tragedies, big industrial accidents in this area with the steel mills, but nothing to that extent.
17 workers were injured in the collapse. Despite rescue workers' best efforts, sadly 13 lost their lives.
That tragic day will always be remembered in the city of East Chicago, because a lot of them saw friends and family or co-workers die as a result of that large collapse.
The city of East Chicago needed answers. What exactly had triggered the tragedy? The first clue was the timing of the collapse.
Concrete was being poured for the deck when the structure collapsed. The additional weight seems to have triggered the disaster, but the structure was designed to be built this way. So the big question was, why did it fail?
Investigators shifted their focus to the temporary steel support towers, the falsework.
Key bolts were missing from the steel frame, as well as wedges that would help align the falsework under the sloping ramp above. There were also issues with the concrete base the tower was standing on.
After the incident, they concluded that the entire sequence of failures started from the supporting pad of one of the shoring towers.
Each leg of the steel tower rested on a 1.5 meter square solid concrete pad, 30 centimeters deep. Dennis McCann is a forensic engineer.
A concrete pad foundation is intended to transfer the loads that are collected in the structure above down into the ground below.
Where the ramp had collapsed, investigators found a pad that was cracked.
If that pad or that footing is too thin or not dimensioned correctly, then it can deflect and deform, which can lead to cracking or performance problems or catastrophic failures.
The problem comes down to concrete's brittle nature.
Concrete failure can be very sudden. In our profession, we call that brittle failure, meaning there's no sign of failure. Just like this, it happened. It's like an explosion.
So here we have a compression testing apparatus, and we're going to conduct a compression test on a concrete cylinder that came from a construction site. It's going to take and apply a force pushing down on that cylinder, and we do that to determine the compressive strength. It's going to eventually begin to crack and will rupture when it reaches its full compressive strength.
The risk of brittle failure is much greater if, instead of being squashed, the concrete is being stretched.
Concrete is strong in compression when it's being squeezed on itself. But unless it's reinforced, concrete can't cope with tension, being stretched or flexed.
With Klein Avenue, it seems the supporting pads were too thin, and when concrete was poured above, they were trying to bend under the extra weight, and one failed.
When the pad fails, the leg being supported by the pad had no support. So it dropped, and of course, the shoring tower tilted. And the support between the shoring tower and the bridge slipped. Now this shoring tower cannot function as it was designed.
That small movement was enough to bring down the falsework, triggering a domino effect along the ramp.
With the investigation complete, construction resumed, and the original Klein Avenue eventually opened to traffic in 1986.
This really emphasizes why testing is critical to making sure that we validate our structural designs and that we make sure we have the correct materials in the field that get built.
Civil engineers learn from these accidents, and structural engineers, in this particular case, have learned a lot.
But this wasn't the end of the story. The first Klein Avenue carried traffic over the ship channel for more than 2 decades. Then, in 2007, the tragic I-35 collapse in Minneapolis triggered nationwide safety inspections, and Klein Avenue didn't fare well.
Inspections revealed it was corroding and becoming dangerously weak. So, In 2009, it was closed to traffic and scheduled for demolition.
But with this major link gone, the area suffered years of congestion. Finally, in 2017, construction began on its replacement, which opened just before Christmas 2020.
This is a new state-of-the-art bridge that will connect Indiana with the city of Chicago. It's going to be primarily used by semi-trucks and companies hauling steel, hauling other products, but it's actually a very much faster and efficient way to get from this area up to Chicago.
With big engineering, safety must always take a front seat. Even the smallest oversight can lead to catastrophe. Like this story in the UK, where a massive highways project sparked a public backlash.
There is a technological room for error, and there's also a human room for error.
A smart solution that may not be so smart after all.
I am absolutely amazed that the biggest safety feature has been removed.
And a state-of-the-art project that risks chaos and catastrophe on the nation's roads. The United Kingdom, a small country that relies heavily on its extensive road network, with more than 38 million vehicles on the move. Former traffic cop Mike Rawson has spent a lifetime keeping drivers out of harm's way.
I'm a retired Metropolitan Police Traffic Patrol Sergeant. The safety of people is an absolute priority in my book.
And statistically, the safest of all Britain's roads are these, high-speed freeways known as motorways. Initially only a 13-kilometre stretch in 1958, Britain now boasts more than 3,000 kilometres in its network, all built with safety in mind.
Britain's motorways traditionally have 4 lanes in each direction, 3 for driving, and the 4th at one side for emergencies called the hard shoulder. They've been that way for decades.
First introduced in the 1980s, these 3.3-metre wide lanes are a safe refuge for broken down vehicles, as well as allowing access for emergency services.
The hard shoulder provides you the opportunity throughout the length of the motorway. If you are unfortunate enough to break down, you can get across to the hard shoulder, and that's the safest place to be.
Hard shoulders have been compared to lifeboats on a ship. You hope you never need them, but if something does go wrong, they're ready.
But with vehicles driving more than 100 billion kilometres on motorways every year, Britain's fastest roads were becoming clogged.
2 main ways to cut congestion are to reduce the number of vehicles with ideas like carpool lanes, tolls, or better public transportation. Alternatively, you could make your roads wider, but that's hugely expensive and disruptive, and in built-up areas, nearly impossible.
In 2006, engineers came up with an alternative. In the biggest change to Britain's roads in decades, the hard shoulder would be turned into a 4th lane of traffic, with computers helping control these so-called smart motorways. The challenge, how to keep drivers safe in case of an emergency.
You can never completely remove the risk of an accident, but if you get rid of an emergency lane, you have to replace it with something that does the job just as well.
Emergency refuge areas were installed at regular intervals along the road. But as head of policy at one of Britain's largest roadside assistance companies, Nicholas Lays explains, it wasn't a perfect solution.
Those refuge areas are spaced at every 1.6 miles. So there may be scenarios where if a vehicle breaks down, it might not be able to reach one of those refuge areas. If you get into a breakdown and you can't reach a refuge area, you might stop on a live lane, which is quite a terrifying experience.
If a vehicle does become stranded, then technology takes over. using the Motorway Incident Detection and Automatic Signalling System, or MIDAS for short. Sensors are embedded in the center of each lane about every half a kilometer. If they detect slowing traffic, the system triggers a change in speed limit on the overhead signs.
By altering speed limits where things are getting congested, the aim is to keep everyone moving as smoothly as possible. It's like air traffic control for the roads.
But although MIDAS can spot slowing traffic, it can't detect stopped vehicles.
A MIDAS system detects slowing traffic, and that can automatically change the speed limit on the variable message signs. But in terms of actually closing the lane physically, that's got to be done by people in the Highways England Control Centre.
For this, operators constantly monitor CCTV cameras, with traffic patrol officers also playing a key role. Friday morning, June the 7th, 2019. Two vehicles were involved in a minor collision on the M1, one of Britain's busiest motorways. They needed to stop, but were too far from an emergency refuge area. Claire Mercer's husband, Jason, was one of the drivers.
They didn't know where to pull over. There was no hard shoulder. The only sign they could see said no hard shoulder for 4 miles. So they pulled over where they could.
The two drivers pulled up against the safety barrier and stepped out of their vehicles. While oncoming traffic moved over to avoid them, critically, the lane remained open.
They couldn't get right out of the left lane because of the crash barrier, and they couldn't stand over the barrier because there was a 30-foot drop onto the road below. So they stood by their vehicles, exchanging details.
6 minutes later, a truck was approaching in the live lane. At 8:15 a.m., still travelling at 90 kilometres an hour, it collided with one of the stopped vehicles. Tragically, Claire's husband and the other driver were both killed.
He was stood there 1 minute and gone the next. Your brain just doesn't work. I couldn't function for 2 weeks, but especially immediately.
Research shows that smart motorways play a role in preventing accidents due to speeding and rear-end collisions. But in this case, the coroner's inquest suggested that the existing system played a role in the tragedy.
This is the coroner's Regulation 28 report to prevent future deaths. The inquest heard unaccepted evidence that the lack of hard shoulder due to the road being a smart motorway contributed to their deaths.
The MIDAS system had neither registered the original accident nor closed the left lane.
The lane should have been closed as soon as Jason stopped, but it wasn't, so the lane was left open.
The MIDAS system, in effect, detected slowing vehicles, but it didn't detect stranded vehicles.
Once the vehicles were stopped in the live lane, it became a race against time to warn traffic of the obstruction ahead.
Part of the problem with these smart motorways is that we've discovered that actually, on average, it takes almost 20 minutes between when the vehicle stops and when that lane is completely closed.
With vehicles travelling on Britain's motorways at speeds over 100 kilometres an hour, sometimes this can be too little, too late.
The risks for drivers increases substantially because if they can't make it to the refuge area, then they're 200% more likely to be involved in a collision than if a hard shoulder were present.
In 2021, the UK government ruled that within 2 years, all smart motorways must include radar systems to more quickly spot stopped vehicles. But many believe that there is only one real solution.
The only answer is to restore emergency hard shoulders, and therefore the moment somebody feels their car is going to fail, they have the opportunity to get straight onto the emergency hard shoulder.
You can say that it's scrapping smart motorways, or you can say that you're adapting smart motorways, but we need a hard shoulder in every single instance.
This is a powerful reminder of the challenges involved with massive infrastructure, particularly when it impacts so many people every single day. The hope is that lessons learned from tragedies like this will make the system safer for everyone in the future.